Oh, sorry about that. I've been blabbering for a couple of minutes. Yeah. Okay. Hello. So do you hear me now? Amateur mistake. I forgot to unclick the mute button. But now I hope it's better. Okay, silly me. But anyway, how was the exam? Oh, that's why nobody's answering me. How was your experience with the exam? It was okay? Oh, nice to hear that. How about the others? Uh-huh. Okay, so we already got your free response up part of the exam. Personally, I'll start grading it later this afternoon, and then tomorrow we'll finish it up. So hopefully by the middle or the end of the week, you'll get it back. So, but another disclaimer, I might not be the one who will be grading your exam because the test papers were distributed online randomly among all the TAs, but you'll be given a little bit of time to to take a look at it and consult with me if you think you'll get or if you should get a higher score. If you feel you should get a higher score on a particular item, just let me know and then I can talk over. I can look over your work and then let's talk about it. All right. Yeah. If you got the low score, well, yeah, I think Fatuma is right. Your final can replace it, so there's still time to make up for it. So, all right. Okay. So today we'll work with or we'll try some integration by parts problem. I was told that you started with it in the lecture last Friday, but I guess for some of you you were preoccupied still with preparations for the test, so you might not have the time to consider some problems with integration by parts. That's why we'll devote today entirely for problems on integration by parts. So I have worksheet 8 here. The second page contains the or some exercises from the calculus textbook. There are 32 problems here. I guess this is enough for you to practice on. Hopefully you'll find time today until Wednesday. And then on Wednesday, let me know if there are some interesting problems that caused you some difficulties so we can discuss them at the start of Wednesday's lab, right? Also, if you have already encountered some IBP problems that are quite hard from the quizzes or from the homework, just let me know in the chat, then probably we can also talk about it today. But let's start with a quick review of what integration by parts is. Well, integration by parts is commonly used whenever you are dealing with an integrand that has a product or a quotient of functions. So here, let me just note that commonly used when integrating a product. Okay, so basically the form is the integral of u times dv. U is a function. dv is probably another function. Okay, not just a differential, but you can look at dv as another function plus the differential, right? And it says here that the integral of u dv, if this integral is hard to solve, I mean, if u substitution cannot solve this integral of u dv, you can use integration by parts, which says that this integral is equal to uv minus the integral of v du. Let's call this formula number 1. Okay, and when applying formula number 1, the crucial part is to choose what is u and what is dv, right? Because if you look, you need to look at the original integral that is given in the problem. So think of it as u dv. So you should identify what function shall we call u and what's the function that will be called dv, right? Because when we apply property number 1 or formula number 1 to this integral, we need the uv in the outside and then the integral v du. Well, what's the candidate? Well, you choose u and dv so that the integral of v du is much easier to evaluate than the integral of u dv, right? So that's why I think this is the most crucial part of IBP. So you need to choose u and dv properly. Some guidelines or some suggestions, you can use the mnemonic islate for choosing u, for choosing the function u, right? This just tells us what is the most likely best candidate for the u, right? So I stands for inverse trig. That's our first priority for the u function. And then if there's no inverse trig, then we'll go to logarithms. And then followed by algebraic functions. Then T stands for trig. And then E for exponential. So the earlier that the letter for the function appears in this acronym, then that means it's the top priority in for the choice of u. And then of course, whatever that remains would be your dv. Okay. So, but this usually works, but there are some rare cases that this won't work, meaning you might encounter some integrals that will not follow this normal isolate convention. Then all you need to do is to try to reverse the choice. Okay. Another guideline that you can use is that u is the function that is easy to differentiate. Or this is has zero higher order derivative. Especially if you will be applying IBP a couple of times, you want u to be something that is easy to differentiate, or something that eventually will have a zero derivative. And then dv, of course, is something that is easy to integrate, or the easier to integrate. So these are my suggestions for choosing the u and the dv. Okay, so just bear this in mind. And once you have the right choice for u and dv, all that remains would be to apply formula number 1 properly and be careful with the grouping symbols. Okay, so I think as always, it's much easier to understand this process by looking at specific examples. So I have here 32 problems that you can pick from where you can pick some problems that you can try on your own. But let me try some. You can also take a look at it right now and then let me know if something caught your attention, and we can discuss them. I'll start first with probably an easy one. Let's try problem number 4, just to illustrate the basic IBP concept. So here we need to integrate x, ln x dx. Of course, we'll try u substitution first. Perhaps that will work, but in this case, u substitution won't work. Whether you choose u to be equal to x or u to be equal to ln x, you cannot get the appropriate form. So we'll go to the next best option, since the integrand x ln x dx is a product of an algebraic function x and a logarithmic function ln of x, then perhaps IBP will work. And remember, isolate, that's our acronym that guides us with the choice for u and dv. The first factor, x, is algebraic. The other factor, ln of x, is logarithmic. And logarithms precedes algebraic functions in the mnemonic isolate. So here I will take u to be equal to ln x, and then dv would be the remaining one, x dx, right? And then I'll compute for du, that will be 1 over x dx. And I'll compute for v. V is found by integrating your choice for dv, okay? So here we'll get x squared over 2. Supposedly there's an arbitrary c, but all you need is one antiderivative, so you can forget about the c for a moment. So now we can use formula number 1. Using formula 1, remember it's uv. So I'll have ln x times x squared over 2 minus integral of v du. So x squared over 2 times 1 over x dx. And we are hoping that this integral is easier to evaluate than the original given integral. And I think it is. Of course, after simplification, right? So let's just rewrite it in a nicer form. So we'll have 1/2 x squared ln x minus 1/2. And then I can cancel one of the x's from top and bottom. So this will just be integral of x dx. And so this is 1/2 x squared ln x minus 1/2 x squared over 2 plus the arbitrary constant c. And you'll have 1/2 x squared ln x minus 1 over 4 x squared plus c. Okay, and this is your integral. Okay, good. And this is the basic one, and I hope this, and I think this is already covered in the lecture, as Rohel pointed out. Now let's try some more complicated ones. Let's try problem number 6. Again, feel free to send in your questions if you have specific IBP problems that you want to discuss. But while waiting for those, let me just pick some problems from the worksheet. Okay, let's try x squared e to the minus x. Well, here again, I'll remember isolate. But again, of course, you need to try u substitution. Perhaps that will work. But in this problem, I don't think u substitution will work. So we need some more complicated technique of integration. And the next best candidate would be integration by parts, because the integrand here is a product, right? And it is a product of an algebraic function x squared and an exponential function e to the minus x. And using isolate convention, the suggested choice for u will be the algebraic function x squared, and the choice for dv will be the exponential e to the negative x dx, right? So after choosing u and dv, you compute du. So that's 2x dx. And v, the integral, is negative e to the minus x, supposedly plus c, but you can't forget the plus c, because anyway, all those plus c's will add up to another arbitrary constant in the end. Okay, good so far? Now, after you have chosen u dv and computed du and v, you are now ready to apply formula number 1, which says the integral is equal to uv, so that's x squared, times negative e to the minus x, minus integral of v du, minus e to the minus x, times 2x dx. All right, so rewriting it will give us negative x squared e to the minus x plus 2 x e to the minus x dx, right? Well, I'm not sure about the other choice, Faiza. Faiza is asking, can we choose u to be equal to e to the minus x and dv equals x squared dx? Sometimes that is also possible. I mean, you can also get a nice integral out of it. But sometimes, if you get the choice flipped, you might get a more complicated integral, right? So I guess for this problem, have you tried it, Faiza, using u equals e to the minus x and dv equals x squared? Looking at that, du will not be hard to compute, v will not be hard to compute, but the only concern is the integral of v du. But probably that will be fine, but I'm not sure. So that's why I'll stick to isolate. So, okay. All right, now we see here that the resulting integral is this guy, but we cannot use u substitution still for this, right? But essentially, so u substitution won't work for this. I'll try another round of IBP. So that's the first lesson here. You can use IBP more than once, especially if the problem calls for it. So the integral here is still a product, so I'll try IBP again. But again, I'll choose u to be equal to the algebraic function x, and then dv is equal to e to the minus x dx. Then I'll compute for du, I'll compute for v, okay? And then I'll plug this in using formula number 1. So I'll copy first the first term, and then the constant factor 2. And then remember, we're applying IBP on this guy. And formula number 1 tells us that that integral is equal to uv, the new u and v. So that's negative x e to the minus x minus integral of v du minus e to the minus x dx. So here you need to be careful with the grouping symbols, right? So what happened there is that this integral was expanded into this guy using formula number 1 for IBP. Okay? So now let's just simplify some things up. So I'll have minus 2x e to the minus x. I have a negative here, a minus here, so that's going to be a plus. There's a 2 outside, so that would be a plus 2 integral of e to the minus x dx. And now this last integral here is easy to evaluate. You can let u to be equal to e to the you can let u to be equal to minus x, du is negative dx, and so on. So essentially, this is minus x squared, e to the minus x minus the second term, and then this is minus 2e to the minus x plus the arbitrary constant c. Okay, so this example tells us that, oh, we can apply IBP more than once, especially if the problem calls for it. All right, any questions so far? Is this good? All right. Now, what if you have a problem like this? This is not in the worksheet, but let me insert this problem here. Maybe I'll use a red one for inserted problems. We'll have x to the 4th, e to the x over 2 dx. Or probably not e to the x. Let me try cosine, because we already did an exponential above, right? So here, picking up the cues from the last example, we have an x squared times e to the minus x. We needed to apply integration by parts twice to get the final answer. But here I have an x to the 4th times cosine x, and then I guess here you anticipate that I will take u to be equal to x to the 4th, and then dv to be equal to cosine x dx. But the thing is, the integral of cosine x will be sine x, and the integral of that would be cosine x, or with a negative sign and so on. So it will just be sines and cosines all over the place. And I have an x to the 4th as your algebraic function. So if the same pattern will occur as the previous example, so that means here I need to use IBP 4 times. And that's going to be a very long solution, right? So, and true enough, if you're patient enough, then yes, you can find the answer using IBP 4 times, right? But for problems like this, I usually arrange my my application of the IBP in tabular form. So here, this is tabular IBP. I'm not sure if you considered in the class or in the lecture tabular IBP. And I find it more helpful whenever I need to use IBP more than twice, rather than doing the paragraph form, writing take u and dv to be equal to such functions, compute du dv, right? Because there would be a lot of grouping symbols that you need to take care of, right? So whereas in the tabular IBP, I can account for everything there in a tabular form. So have you seen this in the lecture, guys? Because if not, then I'll discuss it a little bit slower.
Are you talking about like rewriting it, or are you talking about something else? Because we talked about rewriting the statement equation, but that's it.
Oh, you only did the paragraph form, like what we did in the previous example, right?
I don't know how to explain it. It's like we just like what is it? If it was like the cosine. Well,
she like split it up, you know. You know what I think that's what you're trying to say.
Yeah. So
yeah, something like that.
Okay. So what I'll do here is I'll arrange it in tabular form, because again, remember one of my guidelines in using u is that u is it is more convenient to use as u a function that is or a function that has a zero and a zero derivative later, right? So if you look at x to the fourth, if you carry on the differentiation, you'll get the 4x cubed, then a 12x squared, then a 24x, then 24. Then if you differentiate 24, you get a 0. So essentially, after some successive differentiations, x to the fourth will go to 0, right? And then cosine, not so much. It will just alternate between a sine and a cosine plus those plus or minus signs over there. So that tells me it seems to be more convenient to choose u to be x to the fourth, and dv would be cosine x. But again, this is the same concept as the isolate one, but we anticipate to use integration by parts 4 times, right? But you can arrange your solution in this way in a tabular form. So I will stick to the algebraic function to be the use. And remember what we do with the use, we differentiate them, right? So I'll just carry on with the differentiation here. So I'll have 4x cubed, 12x squared, 24x, 24. Then the derivative of 24 is 0. The derivative of 0 is 0, and so on. So this will be 0 forever, right? And this is what I meant when I said earlier that I want u to be something that that goes to 0 or after some differentiation, right? And then what do we do with the dv's? We integrate them to get the next dv, right? Or to get the next v. Okay, so I'll do that here. Integral of cosine x is the derivative. The integral of cosine x is sine x. And then integral of sine x is negative cosine x. Integral of negative cosine x is what? Negative sine x. And then integral of negative sine x is cosine x. And then integral of cosine x is sine x. And so on, right? Next one would be negative cosine x. And so on, right? I hope I did the integration properly with the signs, okay? And anyway, remember what happens for IBP, we need UV, right? UV, where is UV? So we have UV there. That's our first U and V, right? And then after the next application of IBP, we'll get another UV. And then we'll get another UV. We'll get another UV, another UV. But after the fourth application of IBP or fifth application, we'll get U equals 0 times V equal to dV times V, which is negative cosine x, which will happen from here on. Everything will be 0, right? So that means IBP will stop there. And then remember, formula number 1 has negative integral of V du. So that means there should be alternating signs over here. Okay. And now I can write the final answer. The integral of x to the fourth cosine x dx is equal to the first diagonal product. So that's going to be x to the fourth sine x. And then the next diagonal product together with the alternating sign that I introduced. So that's going to be plus 4x cubed cosine x. Third diagonal product will have negative 12x squared sine x. Next diagonal product, negative 24x cosine x. Next one would be plus 24 sine x. And then that's it. Plus arbitrary constant c, because all that follows would be a bunch of zeros. All right. So you see how I guess this is more compact than the paragraph 4. And you can essentially, we can track the grouping symbols and the signs here much easier than the paragraph 4. Okay. I see, Brian, you sent the question, but I cannot, the picture is not loading. Can you send it again? Yeah, while waiting for Brian's question, anybody else who has a question or a clarification? Is this the method that you are referring to earlier? Or is this a completely new one for you guys? Technically, it's not a new method. It's still IBP. It's just we wrote the solution, we organized the solution in a tabular form so that we don't have to rewrite all those paragraphs over and over again. Because imagine you'll do that 4 times. It's easy to mess up some of the signs over there.
I think we did this in class, just not in the tabular form. So,
Right. Okay. Yeah. So I hope this helps, especially if you expect IBP to be performed more than twice.
Yeah, she did examples that were like repeating at least 3 times, I think. I don't recall 100%, but yeah,
Okay.
we didn't write it how you have it highlighted. That's it.
But at least for me, I guess this is much compact and easier to follow. But again, you need to remember you make the table of the column for you to be the derivatives of your algebraic function that eventually becomes 0, because we want to have a summation that terminates somewhere. And then the column for dv, you obtain it by integrating the previous entry. And then you do the cross multiplication because remember, we need a uv in front of it. But you also do alternating sign. That's where these guys are from. I just introduced them to account for, remember in Formula 1, you have uv minus integral of v du. There's a minus sign in front of the new integral, which complicates things out. So yeah, that's why you need the alternating sign over there. Okay, so I hope this helps, especially if you are having troubles organizing a solution for IBP when this is thrice or 4 times to be done. Okay, I see now Brian's question. So let me know if you have questions with tabular IBP, or perhaps you can revisit it another time next meeting or later today. But I'll go to Brian's question first. It's asking for x cubed sine of 7x squared dx. Now, there are several ways of doing this problem, but I will show you one way, which is using U substitution in conjunction with the IBP. Because for me, that takes care of the complication with the scalar multipliers to the argument of sine. So before I do IBP, well, here I cannot do the tabular IBP as we did earlier because if I will let this to be my U, that's fine because I'll get 2x squared, I'll get 2, then 0, 0, 0, 0, and so on. That's perfectly fine. But I will have a problem letting this to be my dv because we don't have a closed form for the integral of sine of 7x squared. We need to use substitution whenever the function inside sine is a polynomial other than the linear function x, right? So what I suggest here is we do the U substitution beforehand and try and see where it can lead us, or what's the best form that we can get from the U substitution. So here I will let W be equal to W to be 7x squared. Okay. I'm using W because I'm reserving the U later for IBP. So if that is W, then dW would be 14x dx. Or that's equivalent to saying that dW over 14 can be replaced by x dx, right? So knowing that, I'll rewrite the integral as x squared sine of 7x squared x dx. So I borrowed one of the x's from x cubed to go with the dx because I know that x dx can be replaced by dw over 14. Okay. So that means here, I'll start the substitution. I'll change all variables to w. X dx is replaceable by dw over 14. Sine of 7x squared is simply sine w. And then what's left is x squared. What is x squared in terms of w? you can go back to the u substitution over here, and you see that x squared is equal to w over 7. So that means the remaining x squared in the original integral can be replaced by w over 7. So essentially here, we have a 1 over 7 times 14 outside. What would that be? That would be 1 over 98, I guess. Then we'll have w sine w dw here, right? And this is the best form that u substitution or w substitution can give us, right? And you see that in this current integral that we have, we need to integrate a product. U substitution won't work anymore. This is the best we can squeeze out of u substitution. So the next best thing is to do integration by parts, because the integrand here is a product. So here, what do we have? So remember isolate. We have an algebraic function. Then we have a trig function. A precedes t. So our choice for u will be the algebraic function w. And then dv will be the trig function. And then we compute for du. We'll get dw. We compute for v. We get negative cosine w, right? So applying IBP here via formula number 1, right? 1 over 98 times uv, that's negative w cosine w, minus the integral of v du. So that's negative cosine w tw. Okay, you need to be careful with grouping symbols here because it's easy to miss out some of the scalar multipliers or the signs. So we'll have 1 over 98 of negative w cosine w. Let me just simplify it first. So this would be plus integral of cosine w dw, which is fine because we know how to integrate cosine of w with respect to w. So we'll have this. Integral of cosine is sine. And then affix the arbitrary constant c outside. And then we'll revert to the original variable. Remember, w stands for 7x squared. This would be negative 7x squared cosine of 7x squared plus sine of 7x squared plus c. All right, is that good? So here we learned that the integration by parts is not a standalone method. You can use it in conjunction with all other techniques. In particular here, I use u or w substitution at the start just to see the best form I can get out of it. And essentially that's not enough because that gave me the form integral of w sine w, which calls for integration by parts. Any questions, guys? Are you still with me? Questions? Or are you still digesting this? Okay, so it's just it will take a lot of practice, but everything is everything I guess is mechanical after you have the right choice for u and v. So yeah, let's try some more problems then. Do you want to go to the more complicated ones or start with the pretty basic ones first? And I just want to warn you because chapter 8 is a pretty packed chapter because it entails, I think, 3 or 4 techniques for integration. So this is just the first one. There would be a lot more techniques of integration that will be coming your way. So it should be, or you should at least be comfortable using IBP perhaps until Wednesday, so we can focus on the other techniques. But how do you distinguish IBP from the other techniques? Usually IBP is useful whenever dealing with products as integrands. Okay, I don't know what's happening, Brian, but the picture you sent is not readable, at least from my from my point of view here. Let me see if I can see that in the chat. Okay. It's odd. I can see it in my iPad, but in my laptop, I can't see it. Let me just copy this. Okay. Any particular difficulty with this one, Brian? Did you get stuck somewhere? Okay, I guess this is similar to. Oh, do you want to say something? Go ahead. This is similar to what we did earlier. And I guess I can use substitution here. But whenever dealing with definite integrals and you expect that you will use substitution or IBP a couple of times, maybe it's easier to work with the indefinite integral first. So let's solve for the integral of 3x squared e to the minus x dx first. But this is nothing more but ignoring the bounds or the limits for integration, because we don't want to change them every time we will write another integral, right? Because remember, when you change the variables, you should also change the bounds. So I'll worry about the bounds later. So I'll solve for this, right? Probably I can use tabular IBP here. Oops. So I'll make a column for U and a column for dV, right? I'll choose the U's from the function that eventually will become 0 after successive differentiations, and that would be 3x squared. I'll choose dV e to the negative x, okay? And then let's form the column for U by differentiating 3x squared repetitively. So we'll have 6x, I'll have 6, and then after 6, everything now becomes 0, which is good for us. And then the column for dV is formed by integrating the previous entry. So we integrate e to the negative x, it would be negative e to the minus x. We integrate it another time, we'll have e to the negative x. We integrate it once more, we'll get negative e to the minus x. Okay. And then another round, it's going to be e to the minus x, right? And then remember, tabular IBP also requires us to put alternating signs in front of the column for U or for each entry. To answer Bao, it's just that you can use tabular IBP whenever you want, but it's the same process as the usual paragraph form of the IBP that we used for the first example and what you used in the lecture. It's just another way of writing it out. So if you are using it twice or thrice, or you expect to use IBP twice or thrice, at least for me, it's more convenient to organize a solution in the tabular form, rather than the paragraph form wherein I need to write everything out over and over again, right? Okay, but the process is the same. So this is not a new method. It's just another way of organizing repetitive IBP, all right? So I'm done putting the alternating signs. Then remember, I'll need to have the diagonal products. And this is what I like with this, because with our choice of U, we'll eventually have 0 times e to the minus x, 0 times whatever is next, and so on. So essentially, we'll have 3 terms in this answer, or in this integral. So now we can say that the original integral, which is 3x squared e to the minus x dx, is equal to negative 3x squared e to the minus x, and then minus 6x e to the minus x, and then minus 6 e to the minus x, plus the arbitrary constant c. Did I do the cross multiplication right? I hope I didn't mess up the signs. Negative 6x. All good? So let's go back to the definite integral. Remember, we are originally given a problem with bounds in it. And the bounds are, I guess, 0 to 4. So I'll simply plug in 4 first. So I'll have negative 3 times 16 e to the minus 4 minus 6 times 4 e to the minus 4 minus 6 times e to the minus 4 minus, I'll plug in 0. I'll have 0 minus 0 minus 6 e to the 0, but that is just 1, right? And then simplifying this, we'll have negative 48 e to the minus 4 minus 24 e to the minus 4 minus 6 e to the minus 4 plus 6. And then we can add the like terms, everything with coefficient e to the minus 4. So I have minus 48 over here. Oh, this would be minus 30. So I guess we'll have minus 78 e to the minus 4 plus 6. And that's our final answer. Did I do the arithmetic right? Okay, any questions, guys? Does this make sense? Brian, is it fine? All right. Okay, how about the others? Is it okay? Are you starting to get the hang of IBP? You're welcome, Brian.
Kind of.
Yeah, but you see, this is pretty mechanical, so you need to try to practice a lot. So I hope we have 32 problems in the worksheet, so you can take a look at them, try them, and then if something bothered you or something gave you some difficulties, let me know on Wednesday. Probably we can start with a couple of problems with IBP. Right. So another interesting one here is problem 20. Probably I'll stop here. Problem 20 is a little bit tricky. I tried answering it in my previous class and it took us a little while to answer this. So I want to share with you guys this. So here, the only choice you have is to let u to be equal or to take u to be equal to sine root x, and then dv is equal to dx. That's because you cannot take dv to be equal to sine root x because we don't know how to integrate sine of root x, right? So this is your only choice. But actually, if I did my calculations right from my previous class and using IBP, we'll make the integral more and more complicated. But that's the only choice that you have. If you want to use IBP here, this is your only choice for u and dv, right? The other way around won't work, definitely. But if you do this, it will become more complicated. Probably I can show you my attempt earlier. This is from my previous class. And this is what we tried, okay? So I tried that. So after the first IBP, I got this. I got to here. And now the integral of VTU has a root x times cosine of root x. The problem here is this is a little bit more complicated than the original problem because the previous problem doesn't have a root x in front, but now I have. I thought I can use that for a u substitution after the IBP, but apparently I can't because if I will let u to be equal to root x, I need a root x in the denominator, which I don't have at this point, all right? So that caused some problems there. So I tried IBP again. And after I tried IBP, I got this integral to deal with. And this is much complicated than the previous one because before I have a multiplier root x, now I have a multiplier x. And it is at this point that I realized that when I try another IBP, then I will have probably x to the 3/2 sine root x. So I'm getting a more and more complicated integral of VDU if I will carry on with IBP. So this approach using IBP alone is not getting me closer to a particular solution, right? Or to a convenient integral to evaluate. So that won't work. Maybe you can try it on your own later just to convince yourselves that you'll get nowhere near the solution if you'll do that. But this is some trick that we usually use, and I cannot describe why or how I thought of this when I was doing this in my previous class. But this is a usual trick that you'll learn along the way, perhaps by instinct. So if you're doing calculus for a number of years, then probably these techniques will come in as an instinct. But you will only develop the instinct if you try to answer a lot of problems and remember what you learned from each practice problem that you encountered, right? So do you agree this is the same as the original problem, right? Because this root x can be canceled by the root x below, then I'm back to the original expression. But why is this form more useful than the original problem? Because here I can let u to be equal to root x, and then I'll take dv, not let, I will take u to be equal to root x, and then dv would be sine of root x over root x dx. All right. So we don't have any problem with the differentiation to get du, so that's 1 over 2 root x dx. For v, I need to evaluate this integral, right? Because the idea there is to get v. We integrate both sides to get v, right? So in carrying out this integration, you should let u to be equal to root x, and then you'll eventually have 2 cosine of root x, I guess with a negative sign there. Let me double check. If I differentiate this I get a negative 2, and then positive, yeah, sine root x 1 over 2 root x. Okay, right? So again, to find v, I use u substitution. Let u to be equal to root x. You get the integral is negative 2 cosine of root x. Okay. Now I can use IBP now. So this is uv. So I'll have negative 2 root x cosine of root x minus integral of v du minus 2 cosine root x times du. Okay. So we'll have negative 2 root x cosine root x there. Then look at this. 2 will be canceled there. The negative sign there can come out. So we'll have a positive here. Integral of cosine root x over root x dx. And here you can let u to be equal to root x. Du will be equal to negative 1 over 2 root x dx. So essentially this is this. Okay. I need a 2 in the denominator here. So I'll need to introduce a 2 there. Okay. So I'll have a 2 integral of cosine u du after the u substitution. Oh, no, I don't have a negative sign there. Okay. And so we'll have negative 2 root x cosine root x plus 2 sine u plus the arbitrary constant c. And then we'll revert to the original variable, 2 sine root x plus c. Okay. So I just want to share you guys this clever trick that sometimes IBP on its own cannot answer the problem. I think we have seen one example earlier wherein we need to use W substitution first before getting to the IBP. And here another trick is to manipulate the integrand first. See, I started with sine root x. I cannot apply IBP properly there. So I wrote it as root x times sine root x all over root x dx, and then IBP turns out nicely here in giving us a final answer. Okay. Sorry, I went over time by 2 minutes, but I hope this helped. Again, this takes a lot of practice, and I hope you guys will start doing it because Chapter 8 is pretty packed. You have lots of techniques of integration to cover. So try working with problems from the homework or the quizzes. If you have extra time, go over worksheet number 8 and let me know on Wednesday if you still have some problems about integration by parts. Okay, so that's it from me today. So thank you for coming today, and I hope you enjoyed the rest of the day, and let's see each other on Wednesday. All right, goodbye, guys.